Hello everyone, my name is Vimal Prasad and I do come from the School of Mechanical Engineering. Today I'm here to present my research topic. That's the welding procedure for joining two dissimilar metals. That's a creep resistant 2.25 chromium molybdenum steel as well as the AISI 310 stainless steel, which is widely being used in the high temperature applications. Moving further, we do have to answer the question, why do we need a separate welding method to join the dissimilar metals. As we know that similar metals has got similar metal or mechanical properties, which makes them much more easier to develop a welding process for the similar metals. But in the case of dissimilar metals, that the different mechanical properties has to be taken into account. That has to be taken into consideration, and a separate welding procedure has to be formulated for that. In order to ensure that the weld joints is strong, the weldment is much higher. It gives you much higher strength, and it doesn't undergo corrosion or fatigue. Moving on to the table of contents, we do have the introduction chapter and the current welding methods or the conventional welding methods which we are using right now. So we would be taking different elements from the different conventional welding methods, and we would be formulating a new welding technology which would take into consideration all of the weld parameters, all of the mechanical properties of the metals which is used in this experiment. And next comes the factors affecting the strength of the 2.25 chromium molybdenum steel weld joints. So there are n number of factors which would determine the strength of the weld joints of the 2.25 chromium molybdenum steel, and that will be discussed widely. And the similar case applies to the AISI 310 stainless steel as well. And next comes the research question, where we ask the research question on what is the major problem faced, and following it we do have the proposed design for that. And coming down, we do have the limitations and advantages of the research design as well. So let's move into the interaction part. In the introduction part, we do have to discuss about the process of a normal welding technology. As I told before, a normal welding technology includes welding of two metals by heating the weld area, and by heating the weld area would become much more softer, and the softer portions would be joined together, and you will get a much more strong bond. That's what we call in the normal case of welding. And we do have the dissimilar metal welding, in which I've told before that each metal has its own mechanical properties. So based upon the mechanical properties, considering and taking into consideration of the mechanical properties, we'll formulate a separate welding process for that. Next comes the high temperature boiler tubes. That's the area of application of these welding process. So using these welding process, we would develop different kind of weld joints, and these weld joints is expected to do well in the high temperature boiler tubes, because in the high temperature boiling tubes, the temperature would go up in the range of 600 to 1200 degrees Celsius. So within this temperature range, this weld experiment will help us to formulate a better weld formula that would give us a better weld strength for the weld joints. And coming down, we do have the conventional welding method failures we have to take into consideration. And from all these factors which is mentioned in the failures, we would take up the main problem, and we would address the main problem, and we would create a welding method which is less flawless from the previous conventional welding methods. And the major failure which we are facing right now is the corrosion and fatigue. That will be pretty much described in the following slides. And the last but not least is the microstructure evolution. The microstructure evolution is something which shows the strength of the weld joints, which can be clearly shown with the help of the finite element analysis. Moving on, these are the conventional current welding methods which we do have right now. That's the laser impact welding, in which the welding is done using a laser beam. Next comes the electron beam welding. Next comes the submerged arc welding. the friction welding, which is carried out using the friction part of the both metals, and we do have the multi-pass welding, the butt welding, the deep penetration welding, as well as the tungsten inert gas welding. So moving forward, factors affecting the strength of the 2.25 chromium molybdenum steel weld joints. We do have a couple of factors here. The first one is the formation of intermetallic. Intermetallics are nothing but solid components formed through the metal formation, and we do have the internal pressure as well. Internal pressure is a major problem rather than the formation of intermetallic, because if the welding parameters goes incorrect, there is a chance of development of internal pressure. A serious development of internal pressure would create fatigue or corrosion inside the weld joints. Next comes the oxide spallation. We do have the problem of experiencing the formation of oxide layers inside the boiler tubes due to the incorrect weld parameters. Next comes the creep analysis. Creep formation is a nightmare for the weld joints, where when the higher load is applied on top of the weld joints, it tends to break, or it is more susceptible to failure. Next comes the hardness. Hardness and roughness are nothing but the how do we measure the strength of the weld joints. Next comes the factors affecting the strength of the AS3 stainless steel weld joints. In that, we would describe the weld strength, the tensile strength, and the yield strength, which is an inevitable part for the AS3 stainless steel. And next comes the austenite grain growth, which ensures the uniformity in the weld process. And the operating temperatures and the bubble formation are the most important topics which would be considered in this. As you know that you can see the picture which shows the bubble formation. We have got a molten pool here, and we have got a bubble formed beneath that. This would reduce the strength of the weld joints. Next comes the hardness. As we have described earlier, hardness is measured using a equipment called Vickers hardness machine, which would determine the hardness and the strength of the weld joints. Next is the microstructure stability, which would be analyzed using a finite element analysis, and the pre-weld treatment would be done using chromium and the nickel. And here comes our research question. That's to analyze the microstructure variation observed in the cross-section in a weldment, which can prove how strong the weldment performs in a high temperature condition. So here is our proposed design. For this design, I've chosen the submerged arc welding due to an array of reasons, which would say that that would produce less fumes, that would consume less weld metal as well. So the heat input range is in the range of 1.1 to 5.8, and the weld parameters are set to the weld voltage of 24 volts, and the weld current in the range of 550 ampere to 600 ampere as well. And the pre-weld treatment would be done to both metals using the chromium as well as the 2% of the nickel, and this would prevent the metals or the weld joints from getting oxidized or corroded. And next comes the hardness and toughness. As I told earlier, hardness is measured using a Vickers hardness machine, and toughness gives you an idea about the strength of the weld joints. And the finite element analysis is done to find the uniformity or the microstructure. And at last but not the least, we would go into the limitations and the advantages of the research design. First, when we come to the limitations, we do have the limitation of higher weld cooling time. In this proposed design, there is a probability where we do have the higher weld cooling time, and probability of internal pressure formation, as I have discussed earlier. And even the better results could be only obtained after this experiment. After this experiment can be carried out after a long run. And coming to the advantages of it, we do have the lesser formation of the intermetallics, higher toughness and the tensile strength of the weld joints. We do have the better hardness and the less creep formability. That would be an advantage for the weld joints when they are applied with a heavy load. And last, we have the better microstructure. That's the better uniformity of the weld joints, which is found out using a finite element analysis. So that's it. Thank you very much. Thank you for listening.